So Brett, today's lesson is called Lesson 2, Voltage Induced, or Induced Voltage in a Coil. Really, what we're going to look at is this is how a generator works. This is how a generator works. And basically, generators are the negative opposite of an electric motor. Last unit, we looked at an electric motor. We said, oh, if you supply current, you can get something to turn. This lesson, we're going to say, well, if you can get something to turn, it'll create current. So here is a picture of a standard generator, a very simplified generator. We have an armature, a coil. We have a permanent magnetic field, in this case pointing to the right. And we are rotating it clockwise. And we've hooked up a voltmeter to it to try and get an idea of what's going on. The generator was invented by Michael Faraday. I got to pause the video and go on my Faraday rant. So I've done my Faraday rant. Here was what Faraday began to develop, the generator. Now, it's spinning, you can see, counterclockwise in that direction. How is it spinning? Why is it spinning? We are supplying motion. We've either hooked it up to a windmill or a water wheel or something, or you got a human being turning it. But something, we're supplying the motion. And it's going to be easier for us to imagine looking along the end of it. In fact, really what you want to do is look at this picture here on the next page. Okay? And what we're going to follow, Alejandro, is a single positive charge. We're going to follow this positive charge sitting right there in the middle of that chunk of arm, except we're going to do it from this diagram here. Okay? So when that coil is vertical and all the magnetic field is going through it, that positive charge, which is right in the middle of that piece of metal, is traveling to the right. See it? So all of you point your thumbs to the right. Which way is the magnetic field? Magnetic field lines always point from north to south. Which way is the magnetic field in this picture? Which way is the magnetic field? To the right. Now, if you point your thumb to the right and you try pointing your fingers to the right, you'll notice it doesn't work. Now, you know what? Right in this situation, that little positive charge is not feeling a force at all. And if you hooked up a voltmeter, you would notice that your voltmeter right then said 0. But Courtney, it keeps turning, it keeps turning, it keeps turning. In fact, it rotates 90 degrees. So now the positive charge sitting in the middle of that arm is moving straight down. All of you point your thumbs down. Which way is the magnetic field? To the right. So when I do that up here, I get that in this arm, the charges will be coming out of the page towards me. And in the left-hand arm, well, if the right-hand arm is moving down, which way is the left-hand arm moving? Up. You know what? The charges will be moving away from me. And if I go back to my three-dimensional diagram then, here, we would have current going up the left towards us on the right. And you would have, on your voltmeter, the needle would spike, the needle would peg to the right. It keeps rotating. So now, as it keeps rotating, this arm ends up on the bottom. Which way is it moving? That way. Which way is the magnetic field? That way. Oh, you know what? It's moving parallel to the magnetic field, no magnetic force. You'd get a voltage of 0. And then the whole thing, Rob, would start again, except what used to be the right side of your armature is now on the left side, and what used to be on the left side of your armature has rotated all the way over and is now to the right side, and you'll again get a maximum voltage, but in the opposite direction. We'll call that a negative voltage. This is why, even though most of our electronic devices want direct current, this is why we spent a whole unit looking at direct current. Generating and creating alternating current is way, way easier. It's why you get alternating current from the plugs. Setting that infrastructure up, way better. Way better. Okay. Oh, because most of the time for us to create electricity, we're using generators that rotate, that spin. Hydroelectric generators or steam-powered nuclear reactors or whatever. Is that okay? So you go from maximum voltage to 0 to maximum negative voltage to 0 to max to 0 to negative to 0. You get an alternating current. Is that okay, Kimmy? Yeah? Okay. This all walks you through it again. Turn the page. what we want to do today, Zach, is we want to somehow combine that one, BLV, which was moving a rod through a magnetic field, and spinning a coil loop of wire. Do you agree with me that we induce a voltage in both situations? Then let's see if we can link them into one idea. So here's what Faraday thought. Consider the following example. We have a rectangular loop of wire moving to the right perpendicularly to a magnetic field. Where will there be an induced current? And I have location A, B, C, D, E, and F. Which way is the magnetic field, first of all? Out of the page? Okay. What we're going to do is we're going to look at 4 charges. One there, one there, one there, and one there. Oh, but you remember we actually looked at this last day. We looked at moving a coil through a magnetic field, and we did notice that this and this charge here would not induce a voltage because they would both get forced down, but because they were in the horizontal portion of the wire, there was no way they could get forced down. You didn't separate the charges, so we're going to ignore the top and the bottom charges in each of these 6 examples. We are going to look at the back and front charges. The charge at the front of the coil in the middle and the charge at the back of the coil in the middle. Now, in location A, is it even in the magnetic field? So will there be any induced voltage? So let's cross out A, and we can also cross out which location? F. I'm going to come back to B and E in a second. I want to look at location C. Now in location C, I have a charge at the front, I have a charge at the back. Let's look at that charge at the front. Which way is that charge at the front moving? What direction is the V velocity? Which way is that charge at the front moving? To the right, which way is the magnetic field? So can you point your right thumbs to the right? Magnetic field's out of the page. Which way will the front charge feel the force? Downwards? Which way will the back charge feel a force? Try it, please. Which way is the back charge moving? To the right. Which way is the magnetic field? Out of the page. Which way will the back charge feel a force? Also, down. We looked at this last day. We said, you know what? You get a net current of 0. Situation D and situation C are both the same. They're both in the magnetic field. You don't get any current generated. And for the longest time, scientists thought, well, I guess that won't generate a current with a coil then. This is where Faraday, being very observant, comes to mind. Faraday noticed that although he was not generating a voltage or a current with this setup, he noticed as he set up the experiment and as he took down the experiment, the needle moved. He noticed in situation B, as he was moving the coil from no magnetic field into the magnetic field, we have this. Look at the front charge. Which way is it moving? To the right. Is it in the magnetic field? So it will experience a force pushing it which way? Still down. What about that back charge? Is it in the magnetic field? So will it experience a force? So as you're going from no magnetic field to full magnetic field, you're going to get a current rotating clockwise. You will get a current there. Or, if you're Faraday, the needle moved. And then he noticed nothing, 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 nothing. And then when he went to take the experiment apart, when he went to situation E, where he was pulling the coil out of the magnetic field, well, the front charge, is it in the magnetic field at all? So will it experience a force? But that back charge, which way is it moving? To the right? Magnetic field out of the page. Which way will it experience the force? Down the page. And in fact, you'll get a counterclockwise current flowing while you're going from full magnetic field to no magnetic field. While the amount of magnetic field that the area is exposed to is changing, you will get an induced current. And this is what Faraday realized. He realized, aha, magnetic fields don't cause current. The amount of magnetic field passing through a coil doesn't cause current. If you change it, that's when you cause current. There's going to be a delta in our equation. This brings us to the concept of magnetic flux. So to explain this, Faraday realized that a voltage, and therefore current, in a coil was induced when the area of the coil that was exposed to the magnetic field changed. This brings us to the concept of magnetic flux. What's magnetic flux? I'm going to give you Faraday's English definition first. He said, magnetic flux is the number of magnetic field lines passing through an area. There's all sorts of different types of flux. Electric flux is the number of electric field lines going through a given area. Magnetic flux is the number of magnetic field lines going through a given area. Symbol. It's a circle with a line through it and two horizontal bars. For those of you who are Star Wars fans, it's a TIE fighter on its side. Although, to be honest, you're going to notice, Zach, most of the time when we handwrite flux, we don't do the horizontal bars on the top and bottom. We just put a circle with a big vertical line through it. Units, well, all flux is measured in lines, whether it's electric flux, magnetic flux, light flux, and all flux is measured in lines. But the units for magnetic flux, and I think this is the last unit that I'll be teaching you all year, so this may be the last new unit of your high school careers. It is measured in Webers. I think it's double B. Symbol, capital B, lowercase w. Named after a scientist whose last name was? Okay. How do we calculate flux? We're going to see if we can figure it out. Watch. Flux is defined as magnetic field times area. Oh, that's not quite right. If I have the area look up like this, so that the beams of light are horizontal and the area is horizontal, how many, what? I heard somebody say it. We're going to have to add two perpendicular symbols. If they're parallel, you get no flux. So can you add two little perpendicular subscripts to the area and the magnetic field? Okay. And what Faraday realized is flux does not cause current. Changing flux is what causes current. So here's three side view pictures with my high-tech graphics. So for each of the orientation of the spinning loop as shown below, what can you say about the amount of flux passing through the loop? Which of those has the maximum amount of flux? A, B, or C? Vlad? A. Which of those has a flux of 0? And I hope you can see what we're starting to do now is we're starting to relate something spinning like a coil to what we did last lesson, which was just sliding a bar sideways. We're finding a way to somehow start to combine those concepts. Next page. So we want to define, or we want to describe whether the amount of flux is increasing, decreasing, or constant in each case. Let's make a little note over here. Let's remind ourselves that flux equals magnetic field times area, as long as they're perpendicular to each other. What do you think happens in situation A if I increase the magnetic field? Does your flux increase, decrease, or stay the same? Flux increases. How can I increase the magnetic field? Change the solenoid or just move the coil closer to the magnet. Hey, what happens if your magnetic field decreases, like in situation B? Flux decreases. What about situation C, where the area that's inside the field decreases? If you went from all of it being exposed to part of it being exposed, do you think your flux has increased or decreased? Or stayed the same? Decreased? Situation D we're going to come back to. Situation D is a bit trickier. Don't let me forget that. We'll talk about it at the very end. What about situation E if you move from that location to that location? What? You're right. Yeah, here. Or we could say your change in flux is 0, and therefore your current is 0. Nothing. What about F? As this magnet moves closer, the number of magnetic field lines going through that coil, will they increase or decrease? Psst. Will they increase or decrease? Yeah, because it's just like when I move the flashlight closer to the masking tape. You can imagine, hey, more light's going through it now. So flux is going to increase. What about situation G? If we're spinning the coil and we start here and we allow the coil to start to spin in that direction, what do you think is going to happen? Well, looking at situation G, I think actually that's a different view of this right here. Are you not going from full flux to, if it continues to spin, that? So, is your flux going to increase or decrease? Decrease. Goes from max to 0. What about H? What about H? If we squeeze the loop, what happens to the flux? Decreases. What about situation I, where I'm increasing capital I, I'm increasing the current? Well, this is good review for your Friday test. This is the first right-hand rule that we learned. The first right-hand rule that we learned said that if you had a wire that was carrying current, it generated its own magnetic field. How did you figure out the direction? You pointed your right thumb in the direction of the current, and your fingers curled in the direction of the magnetic field, which means above that wire, it's heading into the page, but below that wire, my fingers are curling out of the page towards me. I think below the wire, the magnetic field is that. Yes? Oh, what do you think happens to the strength of the magnetic field if I beef up the current? Bigger. So what happens to the flux? Bigger. Let's go back and look at situation D, the one that I skipped temporarily. Okay. I'm going to tell you that in situation D, the flux is increasing. Now the magnetic field is not increasing. What is increasing is the area. Which area? This is where Faraday had that aha moment. He said, oh, there is an area in this picture. It's the area behind the rod. And if that area is getting bigger as I move the rod to the right, then my flux is increasing. If that area is getting smaller, if I was moving the rod to the left, then my flux would be decreasing. That's the area that we're talking about. That one's not that intuitive, but I've got to give him credit for spotting that. So far, Zach, I've said that you can induce a voltage when you change the field or the orientation or the area in the field. Now I can state that more simply. Do you know when you induce a voltage? You induce a voltage when the flux changes. And that Courtney, now ties in situation D, our last lesson. If you're not moving the bar, is the area behind the bar changing at all? Is the flux changing at all? That's why you're not generating a current that way. If the bar is sitting still, you're not generating a current. Oh, but now we've also found a way to link in spinning, like in situation G. If you don't have a changing flux, you're not going to generate a current. If this is just sitting still, no current. Start it moving, spinning, you'll induce a current. In fact, here's what Faraday found. He found that the voltage varies directly with the flux change. More flux change, more volts. He also found that it varied directly with the number of loops of wire. You want twice the voltage, use 2 loops. You want 10 times the voltage, you know how many loops of wire you should put through there? 10. You want 100 times the voltage, you know how many loops you should put in your coil? 100. Oh, and he found that it varied inversely with time. The smaller the time, the faster you spun it, the bigger the voltage. As an equation, here is Faraday's law. The induced voltage, we'll use our EMF symbol, is given by capital N, where N is the number of coils of wire times the change in flux. What's change in anything? Final minus initial. What was flux? We defined flux as B perpendicular, A perpendicular, divided by the change in time. Hey, that hasn't changed at all. That's been the same since Physics 11. Vlad, you have a formula sheet in front of you. Did I get it right? Yes. No. What? Turns out there's a negative in front. Why negative? Tune in Wednesday. I'll tell you why it has to be negative. Okay. Fine. The reason it's negative is because of Lenz's law. And Lenz's law says that the direction of the current induced by a voltage is created in direct opposition to the direction of the magnetic field that caused the current in the first place. There, now you know. So, as an example, let's suppose we have a circular loop of wire. Quiet, please. Let's suppose we have a circular loop of wire of radius 2.5 centimeters. It's in a magnetic field of 0.4 teslas. The loop is removed from the field in a time of 0.050 seconds. What's the average induced EMF? So there's the picture. We're going from full flux to zero flux. They want us to find the EMF, so our new equation now is negative big N, change in flux over change in time. And Graydon, while this is fairly plug and chuggish, I tend to go back to my DFIC approach for this, specifically because you're going to find it's the change in flux that you spend the most time actually doing the physics on. Let me give you an example. For instance, what's N in this question? How many turns of wire? How many turns of wire? 1. Why 1? You're correct. Who said 1? Show you did? Why 1? Can you all underline the word They'll do that often if they use a singular descriptor. The wire, wire, then assume it's 1 if they don't give you a number. So N is 1. And the other one that's easy to find is the time. What's the change in time? 0.05. What you're going to spend the most time on is the change in flux. And I don't cut corners too often here. I always write what's change in anything. What's my final flux? Why 0? You're right. How many magnetic field lines are passing through that coil once we're out of the magnetic field? None. Minus BA. Zero minus, what's the magnetic field? 0.4 Teslas. What's the area? They're going to give you, I'm going to give you on your test and in questions, one of 2 shapes. It's going to be a rectangle, in which case you're going to go length times width. Or it's going to be a circle, which is pi r squared. If it's not, if it's some bizarre shape, I'll tell you the area in meters squared. Okay? So is this a rectangle or a circle? So the area is going to be pi times r squared. What's r? Don't say 2.5. 0.025 squared. Is the area for a circle actually on your formula sheet? Yeah, it is. I'm going to go to my calculator and type this in. So I'm going to go 0 minus 0.4 times pi times 0.025 squared. The change in flux is pretty small. It's negative 7.854 times 10 to the negative 4. Negative 7.854 times 10 to the negative 4. Units for flux, what's our new units of the day? Webers. I carried an extra sig figure too, Graydon, because I'm going to use it later. Although I've got that number on my calculator, I'm going to use my answer button on my calculator, and I'm going to now start to plug stuff in. Negative. What was N? What was the change in flux? Negative 7.854 times 10 to the negative 4. All divided by, what was the change in time? 0.05. How many volts would this system generate? Negative. Do I need to type the 1? 1 times won't make a difference. But it is going to be negative. I'll put the 1 so I can go times my answer button so I can see what the heck I did. Divided by what, Brett? You don't get many volts here. Well, I only got 1 coil of wire. If I wanted to get 1.5 volts, all I would do is do 100 coils of wire and have a little 1.5 volt generator. But right now I have 1.57 times 10 to the negative 2. Yeah, it's 1 coil of wires. But again, the nice thing about this then, Sebastian, is this really gives us complete control over how many volts we want to generate. When you're designing a generator, okay, how fast do you want it to spin? Or if you're building a hydroelectric dam, how fast do you think you can get it to spin? And then add a big magnet and some coils of wires. Next page. A square coil of wire, 5 centimeters on a side, has 100 turns. It lies perpendicularly to a magnetic field of strength 0.02 teslas. It's rotated through 90 degrees in a time of 2 times 10 to negative 3. What's the average induced EMF? You know what? They want me to find induced voltage. But I'm going to put a little line down the middle of the page because I'm going to spend most of my time finding flux. Hey, Miller, what's N in this question? I did it again. Wow. Done that 10 times. Good gosh. Oh, you candy later on. Austin, what's N in this question? N is not 1. What's N in this question? Okay. I know they said but you got to read the question. So really, it's if you don't see anything like a number of turns, then go look. Did they refer to it by singular? 100. Austin, redeem yourself. What's time? I think that's 0.002, which is faster to type on my calculator. I need the change in flux. Hey, what's change in anything, kiddo? Flux final minus flux initial. I see directions. It says initially we're lying perpendicular, so I think initially we're like this. How many degrees are we rotating it? What does it say? What's our final flux? 0. We can say, I think, final flux is 0. Yes? BA, 0 minus magnetic field of 0.02 area. What shape? Square. What's the area of a square? How do I calculate that? It is based on length times width because it is technically a rectangle. But what do you know about the length and the width of a square? They are the same. Oh, so are you saying we could just go side squared? Is that why we call it squared? Because it's actually based on the area of a square? And is that why we call it cubed? Because it's actually based on the volume of a cube? It is possible. Don't go 5, it's 5 centimeters, so 0.05 squared. I'm going to go 0 minus 0.02 times 0.05 squared. So I get negative 5 times 10 to negative 5. Webers, but I'll store that number on my calculator, and here we go. It's going to be negative 100, negative 5 times 10 to the negative 5, all divided by 0.002. Negative 100 times answer. Now you'll notice we're getting a positive answer. That's because our change in flux happens to be negative and it's canceling out the negative in the original equation, which is kind of nice. Do you get 2.5 volts? So here's the 2.5 volt generator. It would run a small flashlight. So far, Akemi, what we've done is we've changed the flux by changing the area of exposure, usually from maximum to 0. You can also change the flux by changing the magnetic field, because flux is B times A. If they change the magnetic field, because magnetic field, Rob, is a vector, you better make darn sure that you let one direction be positive and one direction be negative. Unless they're both in the same direction, then you're fine. Let them both be positive. But if, well, look at the next question. What direction is the initial magnetic field? What does it say in the diagram? What direction is the initial magnetic field? What does it say in the diagram? Into the page. What direction is your final magnetic field? We're going to have to let one of those be positive, one of them be negative. It says a circular coil with 100 turns of wire is exposed to a changing magnetic field. Careful. as shown below. If the field takes 0.12 seconds to change, what's the average induced voltage? So they're asking me to find an EMF, a voltage. I'll list my data over here. Alejandro, what's N? Yep. And the other easy one, Alejandro, what's time? How do you know? Seconds, yeah. And then Alejandro, I need the change in flux. What's change in anything? Final minus initial. What's changing in this question, the area or the magnetic field, folks? So I'm going to write B final A minus B initial A. You can't have both changing. I won't in Physics 12, but sure, you can have both changing. I don't think I will in Physics 12. I'll have to double check. All right. Now, it doesn't matter which way you let be positive and which way you let be negative. I will take both ways no matter what. But just so all of our work looks the same, do you want to let initial or final be positive? Pick. Final be positive. So out of the page is going to be positive. So we're going to get this. Let's make a little note here. Positive, negative. We decided that. We're going to get change in flux equals. You said the final was positive, show? So 5.4. Area, what shape? Pi 0.1 squared. There's my pi r squared. Minus, you said the initial is going to be negative, so negative 7.8 pi times 0.1 squared. What's the change in flux? You get a change in flux of 0.147? No, Vlad? 0.4147? Like I have there? Did I? I read it wrong, but that's it. 0.4147? 0.4147 Weber. I'll keep that number on my calculator, though. And now it's plug and chug. Negative 100. 0.4147 divided by 0.12. Negative 100 times answer divided by 0.12. Oh, nice! Negative 346 volts. That's a good sized generator. By the way, show, I might have let initial be positive and final be negative. The only reason is that would give me a negative flux, which would give me a negative here, which would cancel out the minus here. I'd get a minus minus. I'd probably get a positive answer. But show, I will take both, because I didn't define which way was positive and which way was negative in my question. Turn the page. Example 6 says, rank the 4 loops below in order of increasing induced voltage. So from smallest to biggest. Loop A, loop B, loop C, loop D. Which of those do you think would have the smallest induced voltage? By the way, what I'm really asking is, which of those has the smallest change in flux? because the magnetic field is the same for all of them. I don't think it's D. Why B? Is its area or magnetic field changing at all? So is its flux changing at all? So how many volts are in B? 0, because change in flux is 0. I think the smallest was going to be B. You can put in brackets Y. Change in flux equals 0. So now that you're figuring out what we're targeting, which of these has the next smallest change in flux? Well, it's either C or D. I'm leaning towards D because what two words did they put after the word squeezed? A bit. I think what they're saying is, yeah, a little tiny bit. I think D would be the next one. There we haven't changed the magnetic field. What we have changed is the area. Which one has the next biggest change in flux? C. Which one would give you the maximum voltage? You'd go from V max to 0. So for what it's worth, technical comment on voltage. For moving wires, use BLV. Although instead of using capital V, we've been using our EMF symbol. And for coils, use negative N change in flux over time. What's your homework? Number 1, number 2, number 3, number 4 are all good. 1, 2, 3, 4. Take a look at 5. I would totally love to do 5 because it's nerdily cool. It turns out, I'm not assigning 5, but it turns out helicopter blades, that's like a coil of wires, and on a dry day, it is spinning through the Earth's magnetic field. It can generate a very large voltage, big enough that I'm told that, for example, in the U.S. military, if they're lowering somebody from a helicopter, like from a Coast Guard helicopter, down to a ship, say, on a cable, the person who's receiving at the bottom of that ship, receiving the person, has to be wearing a grounding harness, or they'll get a nasty voltage shock. So I need to confirm this. I'm not going to assign it, but it is kind of nerdily cool. Wow, helicopters generate lightning to a degree. They build up a big charge, and if you lower a wire, you can be the groundee, and that would not be good. 6 is good. Seven is good. And I got a couple of videos to show you.